everyone. Today we're going to start section 2 of our chapter. We're going to talk about entropy and the second law of thermodynamics. Now this is going to sound similar to the last chapter we covered where we talked about enthalpy and the first law of thermodynamics. So let's start with an introduction. It starts off by saying a statement that we learned in our last lesson. It says, any spontaneous process is irreversible. I'm going to go ahead and star that because if you don't have it in your notes already, it is actually a pretty important topic that I'm going to ask you about on your test. So spontaneous means that it occurs without any outside interference. And these are always going to be irreversible because when we try to go back to our original state, it doesn't take the same exact path to get there. It's not going to do the same exact motion. So to understand spontaneity requires us to understand a term known as entropy. This is a new term. It sounds a lot similar to enthalpy, so make sure that you're paying attention to the pronunciation and what's written on the slide. Enthalpy has to do with heat transfer, whereas entropy is the extent of randomness in a system. So I'm going to underline the term randomness and go ahead and start this definition for you. In other words, how is energy distributed among the molecules of that compound? So we're going to relate entropy changes to heat transfer and temperature. So how do entropy and enthalpy relate to one another? Entropy, if we dig a little bit deeper, is denoted by the letter S. So I'm going to go ahead and star that part. Again, we said this on the last slide. We're just going to reiterate this. It is your degree of randomness. It's going to relate to motion or energy within molecules. A good example of this is if something is more spread out or if something's traveling faster, it's said to have a more randomness to it. A good example of this is the expansion of a gas. When gases expand, they spread out more, so that adds to being more random. They are also faster. They travel faster because they have more energy, and this allows them to move in random motions. In fact, they're going to move randomly around until they hit another particle that's going to bounce in a different direction. Just like with enthalpy, we can also talk about entropy in terms of how does it change. So entropy, again, denoted by the letter S, we can find the change because it is a state function. Let's reiterate what state functions are again. So I'm going to go ahead and draw an arrow because we're going to define it right here. State functions, we only care about the current state, not the path taken to get there. We could have started in Havana and taken several different routes to get to Pekin. There's not one correct way. So we only care about where we started and where we ended. So in order to find entropy change, we're going to do our delta. So this little triangle here means delta, and that means the change. In order to find the change, you always want to take final minus your initial. So I'm going to go ahead and star this because final minus initial is an important thing to know. Okay. Let's break that down a little bit more. When we take final minus initial and we get an S value or a delta S value, what exactly does that mean? Well, if the delta S is large, it means you typically have more randomness, or if it's smaller, you have more orderliness, less random. But we can usually look at this in terms of being positive or negative, just like we did with enthalpy. So I'm going to go ahead and star these and then we'll talk about them. Whenever your change in entropy is positive, this means that entropy is increasing. It's getting bigger. It means there's more randomness in that system. If it is negative, that means entropy is decreasing and that we're more orderly. Another way you could say this is less random. We're going to relate this to what we've learned about in the last section that we just talked about, isothermal processes. Iso, again, means the same, thermal, temperature. So these are processes that occur at a constant temperature. So remember, isothermal processes are when temperature is constant. And here we have, for isothermal processes, delta S is equal to the heat. So remember, heat is denoted by the letter Q. It can be written in the units kilojoules or joules, either one. So heat that would be transferred if the process were reversible. So we denote this by Q with an ReV, which means Q of the reverse. And what we do with that is we divide it by the absolute temperature at which that process occurs. Now, this absolute means that it has to be a positive value, and your temperature is going to be given in kelvins. Most of the time, you will see things written in degrees Celsius. So to go from Celsius to Kelvin, you're going to take your degree Celsius, add 273, and that's going to give you your Kelvin value to use. That statement allows us to set up the following equation. Delta S equals Q of your reverse divided by T. Since S is a state function, we can use this equation for any isothermal process between states, not just reversible ones. Now we're going to talk about delta S for phase changes or isothermal processes. Phase changes. Let's cover them. States of matter have 3 phases, or basically you have solid, liquid, and gas. Whenever it goes from one phase to another, that's considered a phase change. Good example of this are things like melting. So if you go from a solid to a liquid, you are melting. If you go from a liquid to a solid, you are freezing. If you go from a liquid to a gas, vaporizing. If you go from a gas to a liquid, you are condensing. You even have, if you go from a gas to a solid, this is known as deposition. And then if you go from a solid straight to a gas, this is known as sublimation. So you basically sublime. So melting point and vaporization of a substance at its boiling point would be good examples of this isothermal process or these phase changes. There are 2 important ones. I'm going to go ahead and star this for you guys to write down in your notes. The first one is enthalpy of fusion. Whenever you hear the term enthalpy of fusion, which is delta H of fusion, this means when something melts. So I'm going to go ahead and underline that. Fusion means melting. If you ever hear the word enthalpy of vaporization, which is denoted by delta H of vaporization, this is when things are going to be turning into a gas. So again, vaporization is going to be liquid to a gas. So enthalpy of fusion and enthalpy of vaporization are both going to always be positive numbers. These processes, melting and turning into a gas, vaporizing, are endothermic processes. They absorb energy. They're going to have that positive value that we learned in the last chapter. The reason they are positive, where they're going to absorb energy, think about if something melts, it gets that energy from the atmosphere, ice melting. If you're going to turn something into a gas, you have to add more energy, such as boiling a pot of water. Now, delta H of fusion and delta H of vaporization, these can be substituted for your Q of your reverse in your entropy equation. So this is how entropy and enthalpy are being related to one another. We can use our enthalpy values to calculate the delta S of fusion or delta S of vaporization. Now, delta S is always going to be given in the units joules per Kelvin. The reason for this is, if we think about this, if you look at the equation, Q of the reverse, Q is usually given in the units joules. If we think about divided by temperature, temperature is given in Kelvin, so our units is joules per Kelvin. So your delta H of fusion of water, these are going to be important terms, is usually about 6.01 kilojoules per mole. And delta H of vaporization is about 40.65 kilojoules per mole. So I'm going to go ahead and star those. You will need those for your homework. You will also might see them coming up in some examples as well, but they're good numbers for you to write down. Now, we are talking about melting and vaporization, but there are other phase changes we haven't talked about. For example, we haven't talked about freezing, and we haven't talked about condensation. These values are going to be negative because they are exothermic. They release energy. So they are negative because they are exothermic. Think about it. If you want things to get colder, you have to release that heat or release that energy. So since freezing and melting both occur at the same temperature and require the same amount of energy to happen, your delta H for freezing is going to be the same as melting. The only difference is we flip the sign. So instead of being positive 6.01 for melting, freezing is going to be negative 6.01. And again, remember this is for freezing. The same is true for vaporization and condensation. They're the same process, just opposite of one another, and they can occur at that same temperature. So they require the same amount of energy. So if we were going to do the delta H of condensation, it's going to just be the same, but with a negative sign again in it. Negative 40.65 is going to be condensation. Here, this is an example that the book gives us. It says, determine the entropy of fusion for melting 1 mole of ice at 273 Kelvin. Here we have our delta S of fusion, which is the same as saying Q of your reverse divided by T. Now remember, we can relate this and actually change this to delta H of fusion divided by T. So there's your equation we're going to be using. So here we look in our delta H of fusion. We have ice, which is water. So we have to look back. Our delta H of fusion is 6.01. Where did we get that value, Ms. Chastain? Well, if you look, this was one that I asked you to star down for water, 6.01. Okay. So we go ahead and plug that in, and that's in kilojoules per mole. Then we have to plug in our temperature and make sure that it's in Kelvin. Here it's in Kelvin, so we plug in that 273. The last thing that I want to talk to you about before we finish this out is most people are like, well, why did you put this 1 mole here? Well, the reason I put this 1 mole here is because here we have kilojoules per mole. We want our mole value to cancel, so therefore we can get kilojoules per Kelvin that we can switch into joules per Kelvin. Where I got that 1 mole is from our equation. It says melting 1 mole. So if I add that on there, our moles cancel, and that leaves us with kilojoules per Kelvin. Remember, delta S always has to be in joules per Kelvin. So to get there, all we have to do is take our answer multiplied by 1,000, and then we get the answer 22 joules per Kelvin. So let's kind of do an example up here on the board. Here we're going to be given slightly different numbers, and I'm going to kind of show you how you take these numbers and you switch them. So here let's write our equation first. We know that our delta S is going to equal our Q of our reverse reaction divided by our temp. We can plug in, instead of saying Q of our reverse, if we don't know that number, we can say our delta H. It can be our delta H of fusion or vaporization based on what we're doing. So that divided by temp. Let's read our problem. It says elemental mercury is a silver liquid at room temperature. Its normal freezing point is 38.9 degrees Celsius. So I'm going to go ahead and underline that because that's important information. Its molar enthalpy of fusion is 2.29. So I'm going to underline that. And it says, what is the entropy change of a system with 50 grams when it freezes? So I underlined the 4 pieces of information that are the most important. Remember, fusion means melting. And here I'm freezing. So instead of this being a positive number, I'm going to plug down here a negative number. So delta H, I'm going to plug in negative 2.29 kilojoules per mole. Now remember, we're going to divide this by our temperature. Our temperature has to be in Kelvin. Here you're going to see that it's in degrees Celsius. So in order to get that into Kelvin, you're going to have to take 38.9 plus 273, and that gets you 234.1. So 234.1 Kelvin. The last thing that we have to do is we have to get rid of our moles. Well, it doesn't give us moles in the problem, but it does give us grams. Here, you can change grams to moles. So 50 grams, if we want to get to 1 mole, using molar mass. You would have to look on the periodic table and see that mercury molar mass is 200.59. If you divide that, you get 0.249264. And you can go ahead and plug that into the top part of our problem. 0.249264 times delta H divided by T. Here you're going to get the value of negative 0.002438. My units here, I've canceled moles, are going to be kilojoules per Kelvin. Remember, delta S is written as joules per Kelvin. So in order to do that, I have to times this by 1,000 to get the final answer of negative 2.438 joules per Kelvin. Before we move on, I just want to look at this number. One thing I want you to notice is that it's a negative number. So negative tells me that when this happens, that my system is becoming more orderly. Here, I'm going to have you guys try this one for practice on your own. So why don't you guys pause this video and try it. Okay, so let's get talking through it. Here it says our normal boiling point of ethanol is 78.3 degrees Celsius. The first thing you should do is see that that's 78.3 degrees Celsius, and we need to change that to Kelvin. So 78.3 plus 273. For your Kelvin value, that is going to get you 351.3 Kelvin. It wants to know what the entropy change of the system when 68.3 grams at 1 atm condenses. So condensing tells me that this value that it gave me up here for vaporization should be a negative. So I will have to have negative 38.56. The other thing this sentence gave me is it gave me grams. So remember, you have to change that to moles. So 68.3 grams of ethanol. And then we find the molar mass. So we have 1 mole of ethanol. If you were to figure out that molar mass, it is 46.0684. That gives you your mole value of 1.482578. What you do next is you take this information and plug it into our equation. So we have our mole value, 1.482578, multiplied by our delta H, which is going to be negative 38.56, divided by our T value, which is going to be 351.3. This is going to give us the following answer. It's going to give us negative 0.1627333, etc., kilojoules per Kelvin. Again, I don't want that in kilojoules, so I times this by 1,000, and your final answer gets negative 16.27 joules per Kelvin. If you were looking at this, again, we see a negative value. That means, again, our system is becoming more orderly. That brings in the very last part of this. We're going to mention the second law of thermodynamics. So if we're going back over the first law, it says energy is conserved in any process. However, entropy is not conserved. Entropy is the one value that does not, because it does not involve energy, it involves randomness. So for any spontaneous process, the total change in entropy, which again is going to be the sum, your addition of your system plus your surroundings, is going to be greater than 0. So again, the total entropy greater than 0. Because we know that, that leads to our second law, which states that entropy of the universe increases for spontaneous processes, and the entropy in the universe does not change for reversible. So in other words, the entropy of our universe is always increasing. We're continuously becoming more random. So again, our universe is systems plus surroundings, entropy not conserved. Now, while you won't have to do this on a piece of paper, I kind of want to explain the evidence of the second law of thermodynamics. For example, if you have ice at 1 atm at 273 Kelvin, and it wants you to find the entropy of the system, we can go ahead and find that just like we did on the previous slide. Notice that's our system. So 1 mole, 6.01, because it says ice, and if ice is going to melt, that's 6.01. 273 is our temperature, and we get about 22 joules per Kelvin. However, if we look at our surroundings, so our surroundings would be where the ice is in contact with our hand, we know that our body temperature is 37 degrees Celsius or 310 Kelvin. If we use the same numbers and throw in 310 instead, because that's what the surroundings temperature is, and we put a negative in front of that 6.01 since it is melting now, here we get negative 19.4. When you find the total entropy, you're going to see instead of this equaling 0, it actually equals a positive value, showing that our entropy is increasing. Okay. So in other words, again, for a reversible process, 0. Irreversible, it's going to be greater than 0. So as a result, all spontaneous processes, we already know they're irreversible, but we also need to know that entropy is always going to increase. And since we know this information and we have this law, it helps us predict whether something is going to be spontaneous or not. So that's the end of today's lesson. Let me know if you have any questions, and I'll be more than happy to help.